Hi, this video is actually not a part of the lecture series, but instead it contains some preliminaries that may be very useful for you at the moment that you're going to listen to my lecture series. More in particular, it talks a lot about notation. However, we're also going to look at some things which are related to basic statistics that I do think that are important during the lecture series. Maybe you have seen all these things already before, but then this is actually nothing else as just a refreshment of the things that you have already seen so many times before. In order to introduce this, I'm pretty sure that you do already know that econometrics, have had a lot of econometrics before, but econometrics is actually nothing else as applied statistics. And we do already know as well that applied statistics, or maybe in general statistics, is related to probability theory. So therefore, I will talk a lot about probability theory, and I'm pretty sure that you already know a lot about probability theory as well. And one thing that I'm pretty sure of that you already know is that probability theory usually is about so-called random variables and vectors. In that sense, I'm going to use the following notation. I'm going to use capitals for random variables, but I'm going to do exactly the same with respect to vectors. So what I'm not going to do is that I'm not going to use some kind of bold, say, letters that will indicate that we have vectors instead of random variables. I will always use exactly the same notation. And that means that I'm going to use capitals. So for example, y, x, u, and v, they're all going to be random variables or vectors. In that sense, I also have to excuse myself a little bit because of the fact that I already know that I'm going to sometimes, well, mix up a little bit the random variables or the terminology of random variables and vectors. That is to say that I sometimes talk about random variables, whereas in reality, I actually talk about random vectors. I will never do it the other way around, but sometimes I find it so common to talk about random variables that I will talk a lot about random variables instead, in the case that I even talk about vectors. I'm going to assume that the random vectors that we have over here, or random variables, have a dimension equal to q. Well, in general, I will always say what the dimension of q is going to be during my lecture series, and take into account, using this notation that we have over here, that q could be, of course, equal to 1. In that case, these things that we have over here are really random variables. Otherwise, if q is larger than 1, we have, of course, vectors. That's the only difference between the two. Now, we know already a lot about random variables. And one thing that we know for sure is that random variables, in contrast to, say, standard mathematical variables, do not have a predetermined outcome, or at least in general, they will not have predetermined outcome. So even though it's very common in mathematics to say that if you have a, say, non-random variable, that variable could be equal to x equal to 5 or x equal to pi or something like that, that you usually don't do at the moment that we're going to look at random variables, because of the fact that random variables usually don't have predetermined outcomes. But what we do know is that random variables have so-called realizations. And before I say a little bit more about these realizations, let me say that what we're going to do is that we're going to denote these realizations by so-called small letters. So therefore, at the moment that we have this y, x, u, and v as being random variables, then at least preferably, at the moment that I have a random variable y, then I will use the small letter y for its realization. That's not always possible, so therefore will not always be possible to always use the same letter, but what I usually do is that I will use small letters corresponding to the large letters that we have over there. Another thing that we know about random variables is that even though they do not have predetermined outcomes, we do know that they have probabilities with respect to outcomes. And in that sense, it's always good to look at this so-called distribution function, because every random variable is completely determined by its distribution function. And any random variable actually does have a distribution function. And distribution functions, I will always denote them by f, capital F. So this is not a random variable, but it's the distribution function. And in order to denote that a particular, say, distribution function is of a particular random variable, I will always use in subscript the, say, random variable that we're looking at. So in this case, it's the distribution function of this random variable y that we have over here. It is a function, and it's, in this case, evaluated in this little y that we have over there. And by definition, it's equal to the probability that large y is smaller or equal to this little y that we have over there. So that's the idea behind the distribution function. Now, in the case that we are in a special case in which we have a discretely distributed random variable, or vector, of course, then what we could do is that we can write always the probability that y belongs to some subset S that we have over here. So I will generally use, for sets, I will use the notation of calligraphic letters. So in this case, it's just a calligraphic S. So S for set in this case, of course. So this is a, say, a particular set, and it's a subset of RQ. If you have dimension Q, then well, the most that you can actually have is R to the power Q, and it's going to be a subset of this thing that we have over there. And if we would like to calculate for a discretely distributed random variable the probability that y is in this subset S that we have over here, then the only thing that we need to do is that we have to sum over all the probabilities, or actually the outcomes, the probabilities of the different outcomes that we have in this S that we have over here. So this S in this case should be countable, of course, and we're going to be able to take the probabilities with respect to that. So a very simple example, at the moment that we would like to throw a dice, then if we would like to know what is the probability that we throw either 1 or 5, well, that's of course equal to the probability that we have 1 plus the probability that we have 5. Well, this is very simple, of course, for discretely distributed random variables. However, it doesn't work at the moment that we have continuously distributed random variables. And the reason behind that is because of the fact that by definition, a continuously distributed random variable is a variable for which it's always true that any outcome, any probability that y, large y, is equal to this little y that we have over here must be equal to 0. That's the definition of a continuously distributed random variable. So therefore, we can never calculate this thing over here for a continuously distributed random variable. So therefore, we have to use a trick. And the trick is always that we are going to not look at, say, these probabilities that we have over here, but instead we're going to look at densities. And densities are actually nothing else as the first order derivative of the distribution function that we had over there. And then, by definition, what we can do is that we can then calculate the probability that y belongs to a subset S that we have over here by taking the integral of all the y's that belong to this S that we have over there, and then we get our density function multiplied by dy. These two things are, of course, by definition equal to each other if we use this definition over here. So this works all fine. However, the problem that we will generally have is that at the moment that we are going to look at the random variable, then we don't want to say whether this random variable is going to be discretely distributed or continuously distributed. And generally, we would like to make some general statements with respect to the random variable, whether it's continuously distributed or discretely distributed. If we know it beforehand, of course, we can always go for either this notation or that notation. But if we don't know it, then in that particular situation, if we would like to do some mathematics, then we always have to say like, well, if the random variable would have been discretely distributed. And then we are going to use this notation. And then after that, what we're going to do is that we say like, well, and if it would have been continuously distributed, then we are going to use this notation. Preferably, we are going to have just one notation for both a discretely distributed and a continuously distributed random variable. That's actually possible by using the notation that we have at the next slide. We could actually introduce this dfyx over here. And then what we're going to do is that we are going to say that by definition, whether a random variable is going to be discretely or continuously distributed, the probability that y belongs to this set S that we have over here is going to be always the integral over all the elements. And then we're going to get this dfy that we have over there. And we should take into account that this actually could be for a discretely distributed and a continuously distributed random variable. Well, this is relatively simple, of course, at the moment that we have a continuously distributed random variable, because of the fact that we do already know that at the moment that we have a first order derivative, that we can always write the first order derivative by dfy divided by dy. We're going to substitute that into here, then we get exactly the notation that we have at the next slide. But take into account that we're going to use exactly the same notation at the moment that we are going to go for a situation of a discretely distributed random variable. I would like to go on with some additional definitions. And the first definition that we would like to look at is the so-called support. The support of a random variable y equals the minimum set for which fy is strictly increasing. That is the support that we have. You do already know that at the moment that we have a discretely distributed random variable, then at the moment that we would like to look at the distribution function, then the distribution function is typically a step function, at least in the one-dimensional case. And that means, of course, that the moment that fy is strictly increasing, that must actually be a mass point with respect to our random variable. So that means actually nothing else is that the support in the discrete case is nothing else as a set of mass points that we have with respect to the random variable. So for example, at the moment that we're going to throw a dice, well then the support is nothing else as 1, 2, 3, 4, 5, and 6, because these are the only outcomes that we can actually have with respect to a dice. Of course, this also works at the moment that we have a continuously distributed random variable, but then we cannot look at the mass points, but then we simply have to look at where the distribution function is increasing. That's the support. So that means, for example, that for a normal distribution, the support, well, the distribution function is increasing everywhere, so therefore the support is simply equal to the whole real line. The moment that we're going to look at the uniform distribution, well, if we have a uniform distribution in between 0 and 1, well, then that interval is actually going to be our support. Supports are going to be denoted by calligraphic letters. They are sets, so therefore it makes sense to use calligraphic letters over here. But what I'm going to do is that I'm going to be consistent and say that at the moment that, for example, we have a random variable x, then the corresponding support is going to be this calligraphic x that we have over there. So that is the idea behind what we're going to have with respect to support. Well, then finally, and this is again just notation, it could of course be possible that you have two different random variables, for example, y and x, and that even though they're different from each other in terms of outcome, they could have exactly the same distributions. But now we are going to use the following notations. If two random variables or vectors have exactly the same distributions, then we're going to say that they're equal in distribution, and we're going to use this notation over here. It's simply an S, well, with a D above it. I would like to go on with something I would say is going to be quite difficult, but it's something that I'm going to use quite often during my lecture series. So therefore, I do think that it's important to at least refresh your mind a little bit and talk about it. And that is conditioning on another random variable. Well, actually, this also has another name, which is maybe more well known, at least in English, and that is that it is the law of iterated expectation. So this is actually about a lot of things. It is first of all about means and expectations, but second of all, it's also about looking at conditional means and conditional probability. So actually, a lot of things come here together, and finally, what we're going to see is that we can use that in order to derive something that we have here at the bottom of this slide. But let's start very simple, and let's first of all introduce a concept that we haven't introduced yet, and that is the concept of a mean. A mean of a function g with respect to a stochastic variable y is defined as, well, it's actually defined as follows. We usually use for the mean, we use this e that we have over here. And in this case, it's the mean of gy. And that's actually nothing else as an integral over the support of y that we have here. We have here the calligraphic y, of course. And then we have the function gy multiplied by either the density or the probability function of y that we have over there. So this is now going to be our mean as we have it over here. I will introduce this many, many times, and I'm pretty sure that you have already seen this before. Well, in particular, for example, if g is simply equal to y itself, then of course we get the mean of y is equal to, well, you might already have seen that many, many times before. We can do that in the one-dimensional case. In this case, I have assumed y to be one-dimensional random variable, so that therefore this is going to be completely, well, you could say univariate. And of course, this thing that we have over here is univariate as well. It's just a non-random number. But we can do this also for the multivariate case. Then we can also say that the mean of a function gxy, when we now have two random variables, x and y, so therefore this xy is going to be a stochastic vector. And therefore we are going to have a function gxy, which is now of course a function in two variables, multivariate function gxy, where of course this x corresponds to that x, and this y corresponds with that y that we have over there. And then we can look at the mean of gxy. Well, this is a lot more difficult, of course. What is that? Well, the idea is exactly the same. Now we're going to have a two-dimensional integral now over the joint support of x and y that I denote here by the calligraphic letters x, y. And then we're going to get this function gxy that we had already before, and we multiply it then by either the joint probability or the joint density function of this vector xy that we've over here. But take into account that even though this looks a lot more difficult, this has exactly the same idea of what we have over there. Well, now let's go on. This slide I'm going to use a lot because of the fact that I will sometimes, well, make things appear and then disappear again. And let's actually start here at the top again with respect to the mean. But now I'm not that much interested in the mean itself anymore, but I would like to now look at the so-called conditional mean. What is a conditional mean? Well, for that we first of all have to introduce a conditional random variable, that is in this case the random variable y, conditional on the outcome of x equal to x. So we are not interested here, in this case, in the random variable y itself, but we would like to look at how does the random variable behave in the case that we already know that the outcome of another random variable x is equal to this small x that we have over here. Random variables or conditional random variables are difficult to understand, but the easiest thing to understand about conditional random variables is that they're actually random variables themselves. So therefore, they also have means. We call them conditional means. In this case, if we're going to do that with respect to the function g that we have over there, then we can simply look at this mean of gy, conditional x equal to x. What is that? Well, the idea is exactly the same as what we had before. It's going to be an integral of this over y, of the, say, support of y, but now the support of y conditional on the outcome x, that x is equal to this little x. So therefore, I will have here in between parentheses this little x that we have over here. The support, of course, could depend also on the outcome of x, because the distribution function depends on the outcome of x, so therefore the support as well. And then the rest is almost identical to what we had before with respect to the standard mean. It's this function gy, or g evaluated in y, and then multiplied in this case by the conditional density of y conditional on x, this thing that we have over here. Then what we can do is that we can do that for this case, of course, but we can do exactly the same for the same multivariate case. Even though this looks even more difficult, you should realize that compared to the multivariate case, this is actually a little bit simpler. So we can now look at the conditional mean of the multivariate function gxy with respect to a stochastic vector xy conditional on x equal to x. What is that? Well, that's of course by definition equal to the mean of gxy conditional on x equal to x. I haven't done here anything yet. I just have, well, introduced here the conditional mean over here. However, as I already said, even though this looks a lot more difficult even from the multivariate case that we had before, this is actually becoming simpler. And the reason behind that is because of the fact that even though this still looks like a mean of the random variable, or actually better to say the random vector xy, that's in fact not true. And the reason behind that is because of the fact that this is a mean where we assume that we already know that the outcome of x is equal to little x. So therefore, even though I write here x as a random variable, we already know what the realization of x is. We know that it's equal to this little x that we have over here, whatever this little x of course is. So that means that I could actually also have replaced this large x by that little x that we have over there, because of the fact that these two x's are of course identical to each other. So therefore I can also use this notation that we have over here. Well, then things become a lot more simple, because that implies that this mean that we have now over here is actually no longer a, say, mean with respect to x and y, but it's only with respect to y, because I only have here a capital Y over here. So this is actually nothing else as a mean over y, of course, conditional on x equal to x. That means that it's almost identical to what I have over here, with the only difference that I will not have the function gy over here, but of course the function gxy. But it's going to be a one-dimensional integral over here, not two, because x, we already know what it is. So therefore we don't have to integrate out with respect to x. We only have to integrate with respect to y, and we are going to have this function over here. Take into account, as I already said, this thing that we have over here is exactly identical to that thing that we have over there, with the only difference that we have here the given x in our, say, function definition. So this is all fine, of course. Now, what I would like to do is that I would like to actually now go back to a thing that we already had, and that was this mean that we had over here. Remember that we started actually with this multivariate mean, with at least with respect to a vector, and we had already this part that we had over here. I would like to go back to this thing that we have over here, and I would like to rewrite it a bit. How can I do that? Well, that I can actually do by realizing that a conditional density or conditional probability function is always equal to, well, this is something that we already know. If we are going to condition on something, then it's always equal to the joint divided by the marginal. So in this case, if we have a density function, then it is going to be the the conditional density function is equal to the joint density divided by the margin, in this case, on which we are going to condition, and that is in this case equal to x. We can rewrite this, of course, because of the fact that what I can do is to multiply the left and the right hand side by dfx, the thing that I have here in the denominator. And then what we're going to get is this relationship that we have over here. Well, that's very nice because of the fact that this part that I have over here is exactly equal to that part that I have over here. It's 2 times the joint density function. So therefore, what I can do is to substitute this into there. Then I get actually the last line that I have on this slide. So that's this thing that we have over here. This looks still quite difficult. Actually, I've made it even more difficult. But one nice thing with respect to this notation is actually that I can now actually use 2 different integrals. Take into account that this is actually an integral over a full set of x and y's. But now what I could actually do is to write first a, say, integral over the x's, and then over the y's, conditional on the x's, because of the fact that I have here the conditional density. So I'm actually going to do that simply by using parentheses. So here I have here an integral over x instead of an integral over x and y at the same time. Then I have here my dfx that I already had over here. And then within parentheses, I have now an integral over y, conditional, of course, on x. And then I have all these things that I already had before. Even though this is just a simple way of rewriting, we should realize that this works actually pretty fine. And the reason behind that is because of the fact that we should remember that we actually did have that this thing that we have here in between parentheses is exactly the conditional mean that we had before. So that means actually nothing else is that what I can do is substitute this formula that I have over here, this equation over here, into there in order to get the final thing that we have over here. And why is this so nice? Well, this is nice because of the fact that this thing that we have here at the left-hand side is in many cases extremely complicated. This is a mean of 2 random variables of this function that we have over here, and then we get an integral over both the support of x and y. In many cases, that's extremely difficult to calculate. However, this conditional mean might be much easier to calculate in many situations because of the fact that it's just a mean of y conditional on the x's. So therefore, in many cases, it could be much simpler to first of all calculate this part that we have over here, and then simply to do that, of course, for any x, any small x that we have over there, and then simply integrate out with respect to the x's to realize that then we get this thing that we have here at the left-hand side. To give you a very simple example of this, we could have a situation in which gxy is simply equal to y. Well, then we see that the mean of y is actually nothing else as the conditional mean of y conditional on x equal to x. Why would we do this? Well, in some cases, it is relatively simple to calculate the mean of y conditional on a particular level of x. And then the only thing that we still need to do is to integrate over the x's in order to get our mean of y that could have been quite complicated. Okay, let me go on with the next topic. And let me introduce this topic by saying that very central in statistics, but of course also in econometrics, is to estimate parameters of models. Well, this might not always be real parameters. They could also be objects that are derived from these parameters. But in many cases, as you may already know, what we would like to do is that we would like to estimate things, whatever they are. But now we should realize that parameters are usually denoted by a Greek letter. The only reason why I actually say this is because of the fact that later on I'm going to use notation where I'm going to use these Greek letters over there. Maybe more important is to remember one important thing, and that is that you should realize that there is a difference between so-called estimators on the one hand and estimates on the other hand. That is to say that estimators are always random variables, and they should always be treated as random variables, so they do not have predetermined outcomes, while estimates are realization. And I do think that this is actually, if econometricians have to know something, then this is one of the things that you actually need to know. In order to understand this even a little bit better, the first thing that we can ask ourselves is, what are actually estimators? Well, what you can say is that if you would like to give a description of estimators, then estimators can be simply described as being recipes to estimate something based on data. In that sense, it's good to compare it with other kinds of recipes, such as recipes that you usually have at the moment that you would like to cook or bake something. So suppose that at a particular moment in time you would like to bake an apple pie. Well, then what you typically do these days is, well, in the old days, you would typically go to search for a cookbook. Nowadays, what you typically do is that you go for Google and you will find a nice recipe. Now you should realize that these recipes themselves, what is written down in Google, at least what you get actually from Google, these recipes are of course not the apple pie. You cannot eat it, but you should take into account that if you have all the, say, ingredients that are described in the recipe, and if you're a good cook in a sense that you follow all the, say, things that are written down in this recipe, then if you do this all correctly, then in the end you will have something that looks like an apple pie. So, and that is actually the same with respect to estimators. We should realize that estimators, they're also recipes, so they're not estimates. They're not, say, numbers or something like that. They're not numbers that are related to the things that we want to estimate. They're actually nothing else as recipes in order to estimate something at the moment that you do have a data set. Now we should realize that what we typically assume is that our data comes to us in a random way. So what we usually assume is that data for us is random. It's a random factor. And that means, of course, that since estimators are recipes to estimate something based on data, they are functions of data. And therefore, they are random themselves. Beforehand, before we actually get a data set, a realization of our data set, we have no idea what our estimators are going to be. And therefore, they are random variables. However, it may be possible that at a particular moment in time, you will get a realization of your data set. That is, in fact, the thing that you have on your computer usually. Well, then what you can do is that you can follow all the steps related to the estimator. And then what you get is something that we call an estimate. So estimates are numbers. And they're not, of course, random because of the fact that they're realized numbers and they're our realizations of our estimators. I would like to go on with the next topic, and that's the topic of convergence in probability. Actually, I don't need convergence in probability here so much, but I need it in the end to discuss some other things, especially what is written down here at the bottom of this slide, and that is related to the so-called properties of estimators. If we have an estimator, then we would like to know whether that estimator is actually a good estimator or not such a great estimator. And for that, we need criteria or properties. Well, in order to introduce this, as I already said, I need to look at the convergence in probability. But before I can do that, I first of all have to make another definition, and that's a relatively simple definition. That's when the definition of a random sequence. Random sequence Bn is a random variable that depends on n. It is as simple as that. What does that mean? Well, we already know that random variables, they do not have predetermined outcomes. And another thing that we already know from a random variable is that they are completely determined by their distribution function. So that means, of course, that if a random sequence depends on n, well, that of course doesn't mean that, since it's a random variable, that the outcomes depend on n. What it actually means is that the distribution function of Bn, of course it has a distribution function, depends on this n that we have over here. Where n, by the way, I haven't said that yet, typically is denoted as our sample size. Let's look at a very simple example of a random sequence. That is the so-called sample mean. And a sample mean is actually nothing else. Well, I'm pretty sure that you have already seen this before. It's the sum over all our observations. In this case, we only observe y, and we divide by the number of observations that we have. It's immediately clear that this thing that we have over here, well, at least the distribution function of this thing that we have over here depends on n, even though we will know in general that the mean actually of this thing that we have over here doesn't depend on n, but the variance does, because of the fact that, well, a random variable that changes with respect to the variance also changes with respect to the distribution. Therefore, also the distribution function here depends on n. Everybody knows that the variance of this thing that we have here on the right hand side is going to be much larger at the moment that we have only 10 observations than the moment that we have 10 million observations. And therefore, this Bn depends, the distribution depends on n, and therefore it's a random sequence. Then the next thing that I would like to do is that I would like now to look at the so-called definition of the convergence in probability. Now, as an econometrics professor, I do already know that the definition of the convergence in probability, or at least to explain it, is one of the most difficult things to do. One of the reasons behind that might be because of the fact that I even find it quite difficult to understand the concept of convergence in probability. So therefore, what I will actually do here is that I will do this in two steps. The first thing that I will do is simply write down, or actually read down, the things that I already have written down over here. And then the next thing that I will do is that I will try to, in my words, try to describe what it actually means. So let's do the first thing. That's not that difficult. What is the definition? Well, the definition of convergence in probability is the random sequence Bn is said to converge in probability to B whenever, for every epsilon larger than 0, we have that the limit, in the case that n goes to infinity, of this probability, it's the probability of Bn minus B in absolute values, smaller than epsilon, is equal to 1. Well, this is, of course, an extremely difficult definition. And the reason behind that, maybe not so much related to this part over here, but especially related to this part that we have over here. We have here a limit of n going to infinity. I always find limits myself already quite difficult. And then we even get it with respect to some probability. And then for an epsilon, that can be anything larger than 0. And that limit in the end needs to be equal to 1. What does this mean? Well, in order to understand what this means, maybe the best thing to do is to actually ask ourselves first, what does it actually mean when a non-random sequence converges to something? To give you an example, this is an example that you of course know all from calculus. We are going to look at the non-random sequence, for example, 1 over n. That's a non-random sequence. We do know that if n goes to infinity, that then of course this random sequence is going to converge to 0. But what does that actually mean? Well, we know from calculus that that means actually nothing else is that for any epsilon larger than 0, we must have that the absolute values between our random sequence and where it's going to converge to must become, say, we must have an n in such a way that if n becomes larger than that n that we have, that the difference becomes smaller than that, say, arbitrarily chosen epsilon. So therefore, you could also phrase it as follows. If somebody is going to give me an epsilon, then the only thing that I need to do is that I actually give an n in such a way that if the real n is going to be larger than an n that I'm going to give, then the difference between my sequence and where it's going to converge to in absolute values should be smaller than epsilon. Let's give it an example. Suppose that we are going to look at 1 over n. We do know that that converges to 0. So suppose that somebody is going to say like, well, I would like to have that epsilon is equal to 1 over 100. So the difference should be smaller than 1 over 100. Well, that's not so difficult, because then I can say like, well, then n must be larger than 100, because of the fact that then 1 over n, if n is larger than 100, minus 0, well, that's smaller than 1 over 100 in absolute values. And of course, somebody could say like, well, but I would like to have it 1 over 1000. Well, then I just take n equal to 1000. Well, this is all quite simple. Why is this important? Well, this is important because of the fact that we would like to do something the same at the moment that we're going to look at probabilities. But with probabilities, we have a problem, because of the fact that if we're going to look at a random sequence, then the problem with respect to a random sequence is that a random sequence doesn't have predetermined outcomes. And that means that we cannot talk about the difference between, say, Bn and B. And the reason behind that is because of the fact that we do not know what Bn is. So talking about the difference between Bn and B, that is as good as impossible. So therefore, we have to use a trick here. And the trick is always the same in probability theory, is that instead of looking at, say, the difference in this case itself, we're going to look at the probability of the difference. And that's exactly the reason why we have here this probability of the difference between Bn minus B. And what we're going to say over here is that even though, of course, we do not know what Bn minus B is, what we want to have is that the probability that the difference between Bn minus B is going to be smaller than any epsilon that we have over there, if n is going to converge towards infinity, that probability should be going to 1. So that means, of course, that it's not necessary that this difference is always smaller than epsilon. We don't know that. So therefore, we can actually not know whether this difference is smaller than epsilon. But we can, of course, calculate the probability. And the only thing that we need is that if n goes to infinity, take into account that this is actually a non-random sequence, that should actually go to 1. So then we can use our knowledge about non-random sequences, and the only thing that we need to do is to show that this non-random sequence is going to converge to that one that we have over there. And that means actually nothing else is that, well, if n goes to infinity, then the probability that Bn minus B is smaller than epsilon is going to be going to 1. So then we actually get, well, something that becomes non-random. Well, I hope this was clear. Then something about the notation. At the moment that Bn is going to converge to B in probability, then the notation that we're going to use is this Bn, and then we get right arrow to this B that we have over here, and we put a P above it. I'm not going to use this notation, by the way, often during my lecture series, but the next thing is more important. Suppose that we're interested in a particular parameter, and we would like to estimate that parameter by an estimator theta hat n that we have over there. This is very common notation. At the moment that we have a parameter and we would like to estimate it, then we know the estimator by a theta, well, just the parameter by itself, but with a hat above it. Well, then at that moment in time, we say that the estimator theta hat n is consistent whenever theta hat n is going to converge in probability to theta. We know, of course, that since estimators are random, it is very unlikely that our estimator is exactly equal to this parameter that we have over here. That's also not something that we're going to require from any estimator. The only thing that we're going to require is that at the moment that n goes to infinity, so if we have the total population, then in that case, we are going to see that our estimator should converge to the real thing that we want to estimate. And that is consistency. Consistency is extremely important in econometrics. Let's go on with something else which is important, and that is the law of large numbers. The law of large numbers, well, suppose that we know that we have a random or a sequence of random variables that I denote here by yi, and suppose that they're iid, so they have all the same distribution. And in addition to that, I'm going to assume that the mean of y1, so the very first one that we have over here, but therefore of all the others, because of the fact that they are identically distributed, the mean of y1 is equal to mu, and that's smaller than infinity. Well, then if we are going to define our sample mean, well, that I denote by yn over line, that's again simply equal to the sum of all the observations divided by n. But then you can show that under these conditions that we have over here, that yn over line is always going to converge in probability to that mean that we have over there. So this mu that we have over here, which says nothing else is that the average of a, say, random variable is going to converge to its mean. Well, this is very important, but it's especially important because of the fact that there is actually an extension of this law of large numbers. You could actually say it's nothing else as an application of the law of large numbers. It directly follows from the law of large numbers, but in econometrics, because of the fact that it's so important in econometrics, we usually call this the analogy principle. What is the analogy principle? Well, suppose that we can write down our parameter of interest, so this theta that we have over here, as the mean of y with respect to a function g that we have over here. We already know what this thing is because we have introduced that before. And we do know that that's actually nothing else as an integral over the support of y, this y that we have over here, of our function gy, and then multiplied by either the density or the probability function of y that we have over there. Suppose that it's possible. So this is not always possible, of course, but suppose that it's possible that we can write our parameter as this, what we typically call population mean of y. If we are able to do this, then it's still not that clear directly how to estimate this thing that we have over there, because of the fact that this thing that we have over here is not known. You should realize that this thing that we have over here, even if we can theoretically write it like this thing that we have here is not known unless, of course, we know the distribution of y. But that's something that in general we do not know as econometricians, because we don't usually assume that we know our data distribution. So then the question arises, if we don't know this whole thing that we have over here, how do we actually get that parameter? Well, we cannot calculate it, but we can try to estimate it. So therefore the question arises, how do we get a good estimator of this parameter over here? Well, the analogy principle says that it's very easy. The only thing that we need to do is to replace this mean, this population mean that we have over here, by its so-called sample equivalent. That means, in general, that instead of taking expectation, we're going to take summation over all the observations that we have in our analysis, so the n observations that we have, and then we are going to evaluate the g function in y, so not y itself, but actually the observations of y, and we divide by. This is going to be the sample equivalent of that thing that we have over there, for whatever the function g that we have over here. If we then are going to define theta hat as being our estimator, then the analogy principle, and that's completely or directly related to the law of large numbers, then the analogy principle says that theta hat is going to converge to theta. Well, that means, of course, that theta hat n is going to be a consistent estimator of our parameter. And because of the fact that it's so important to get consistent estimators in econometrics, that implies that this analogy principle is so valuable.